Okay, guys, we're going to do a mechanics question today, just on particle equilibrium. Hopefully, you're going to see why this is rapidly becoming one of my favorite step topics. I really like these questions. Okay, all we have really to think about here is a cylinder like this, with the particles on the outer surface of a cylinder, and they are connected by a string like that. And at first they're in equilibrium. So if we draw on the center of the cylinder, this one is P, this one is Q, and the line between them is like that. Okay, so that's really that information there. Both particles P and Q have masses 3m and 4m respectively. Let's draw on little arrows to show that. So that would be our force being 3mg, and this is our force vertically downwards as well, being 4mg. Okay, so they lie on the outer surface of the smooth cylinder of radius A. I should mark that in as well. So there we go. Its axis is fixed and horizontal. So that just means we're looking at a slice through the cylinder. And this is completely horizontal, so there's no weird, the cylinder isn't placed like this or anything. That would make the question significantly more difficult, because then the particles would be coming down like that. So that's not the case. It's actually simpler than that. So they're connected by a light inextensible string of length a half pi a. Alright, well, what does that tell you? That tells you the length, that string there, connecting P to Q, is of length pi over 2 times a. Okay, so can you work out this angle here? It must be a right angle, right? Because, that's just, it's pi over 2 multiplied by a. It's like the radius is just going to be pi r in that case. So that's like a quarter of 2 pi r. Or whatever way you want to think about that. Spotting that really helps this question. Makes it like a lot easier. So they all lie on a vertical plane perpendicular to the axis of the cylinder. Axis intersects at O. Now we're told initially the particles are in equilibrium. So what does that mean? Well, we can think about this in a number of ways. We can start resolving forces and stuff. I'm going to draw the rest of the forces in now. We're going to have, the reaction at Q completely vertical to the surface of the cylinder, and the reaction at P. Alright, and then we're going to have tension in the string, of course. And the rest of the results will come from resolving the weight there. Okay, so we're probably going to do that at some point. But what would be easier to do when you're told the system is in equilibrium, this is something that was quite new to me, was you calculate the gravitational potential energy of the system. Now notice that is the only energy the system will have at this point if it's at equilibrium, right? And what's true is you can differentiate that with respect to any parameters that might be varying. So in this case, I guess an angle, theta, and set that equal to 0. And you will get a particular value of theta for equilibrium. So what that means is the gravitational potential energy is at either a minimum or a maximum. And what that means is that the system is stable. Okay, it's in equilibrium. It's either in unstable equilibrium or stable equilibrium. Okay, so stable equilibrium, I think it's when the energy is at a minimum, which means that if you disturb it slightly, it'll go back to that point. Think of it like this. Think of the energy being like this. If you disturb it slightly, it'll return. But when the energy is at a maximum, energy wants to go to the minimum. So when you disturb it slightly, it will come off and roll down. So, in short, we can answer this question by finding an expression for the gravitational potential energy. So if we find that, it's given us actually the angle theta, and it's between OQ. So if we draw a line like this going up, then this here will be theta. Okay, so all we have to do now is find an expression for the gravitational potential energy, which we can do. So if we think about that, then we just have to calculate the height. I guess we could take GP to be 0 through the center of the cylinder like that. So that's GP 0. And we just have to now calculate the height. So if you notice the height there for Q, that's just going to be 4mg. I think that's going to be cos. So that is going to be, 4mg cos A. Okay. And then similarly for P, we know that angle there is actually 90 minus theta. Sometimes I like to write that as theta complement, rather than writing like pi over 2 minus theta and all that stuff. So we're going to have that plus, and I believe that is going to be 3mg sine theta times A. So we basically know that this expression for the gravitational potential energy, if I was to differentiate that and set that equal to 0, I'm going to find a particular value of theta such that the system will be in some sort of equilibrium. So we're just going to go ahead and do that. We're going to get minus 4mg A sine theta plus 3mg A cos theta. Okay, and I'm gonna give this particular value of theta a special name, right? But I mean, first of all, this is 0, so we're going to cancel the mg's. They're all positive constants, so that's fine to do. Now taking the sine over the other side and then dividing across by cos, because we know that theta, realistically, theta is not going to be pi over 2. Right, and why is it not going to be pi over 2? Well, because it's still in contact with the cylinder. We can just assume that it's never going to reach a point where the particles are like this. We would assume in our model that Q would have left the surface of the cylinder by that point. So this is going to be, if you solve that equation, you're going to get tan theta is 4/3. No, you'll get 3/4. Because, yeah, you'll get 3/4. That's okay. Yeah. So that particular value of theta is such that tan theta is 3/4. I'm gonna call, I don't know, the initial theta, because that's when the particles there are initially. And later in the question, I might need to work out the sine and the cos for that, but rather than doing all of that, I can just draw this triangle and then refer back to it. This is a cool trick you might have seen before. So I'm just gonna have 3 there and 4 there. So that's just using the information that tan of the opposite over the adjacent is gonna be 3/4. And then, this is just gonna be 5 by the Pythagoras rule. And then we can derive sine and cos very easily from it if we need to. So sine theta I in this case is gonna be 3/5, and cos theta I is 4/5. So that might be helpful later. But yeah, so far, having that trick when we used this property of differentiating the gravitational potential energy, that was very neat. Okay, so yeah, that's interesting. Now, as the particles are moving, what's going to be happening now? Well, they're going to have kinetic energy now. This system will have kinetic energy. What we can say is we can say that the kinetic energy of the system plus the gravitational potential energy of the system, this has to be equal to a constant. Moreover, what constant will this be equal to? Well, it'll actually be equal to the GPE initially, because what will happen there is basically as the particles move, all that gravitational potential energy they had at the start in equilibrium, some of that will just be converted into kinetic energy. Some of it will stay where it is. But that is the energy of the system. And we can actually find that now because we know what theta I is. So this is our expression for the gravitational potential energy. And we know that theta I is 3/5, and we know that this is 4/5. Okay, so we calculate that to be 16 MGA over 5 plus 9 MGA over 5. And that gives me 5 MGA if my maths is correct. So that is the total energy of the system. Okay, so I'm going to put that on the right hand side. Now on the left hand side, I want to calculate the kinetic energy, which is quite easy to do, because when these particles are moving, they're just moving, and they will have kinetic energy given by just the change in that angle there, theta. Okay. In other words, the speed of the particle, I can just write that as well, this is v squared. But what is v? Well, you should know that in the formula booklet, if we consider the speed of the particle, that's just going to be a theta dot, right? So I'm actually going to be squaring that instead of v squared. Both particles will have the same kinetic energy, so I can just group that together. That's going to be half of their masses, their combined masses, which is 3 plus 4, giving us 7. So that's just going to be an expression for the kinetic energy of the system. And for the gravitational potential energy of the system, I have that expression there. So that's 4 MGA cos theta. And this time theta is varying. Okay, so we have all of that. And we're nearly done now. I guess we just gotta cancel some constants. And we're gonna multiply across. So, what's common here? Well, in each case we're gonna have, sorry, there should be an m there. In each case we're gonna cancel the m. We're also gonna cancel one of those a's. Okay. So that'll give us a theta dot squared. So that I'll go, this I'll go, this I'll go, and we're just going to multiply across by 2. So that's going to give us 7 a theta dot squared plus 8g cos theta plus 6g sine theta. And multiply over there by 2 equals 10. All right. I think that's what we want. Yeah. Okay, so that's fine. So we have that to be true. Now, next bit is given that Q loses contact with the cylinder first. So as this bead system of particles or whatever will move, what will happen is at some point the reaction at Q will go to 0. And that'll happen before the reaction at P goes to 0. So, I mean, the whole crux of this question is really realizing that this equation here holds all the time right up until one of the particles will lose contact with the cylinder. So at that point we can still use that equation, but after it becomes redundant. So Q loses contact with the cylinder first, show that when it does. So we can still use that equation. Similar to the next bit, while they're in contact. So we can still use that equation that we've now derived. Now, what we can do is we can set up an equation such that when Q loses the reaction, well, what is the force? can we resolve, what can we do in F equals ma for that? Can we do Newton's second law for that, right? So what you're going to get is, try right up here, it's 4mg minus, that's 4mg, and then you're going to resolve that, so it's going to be 4mg cos theta. Okay, you're going to be taking away your RQ, so that's force equals mass times acceleration, right? So that's going to be the mass of the particle, which is 4m. Now the acceleration is, in this case, radial, right? So that's m a theta dot squared. So that's your radial acceleration that you have right there. Okay. So hope we're comfortable with this equation. So really, all we have to do is take this equation and set RQ to be 0, right? And if we set RQ to be 0, we will have 4mg cos theta is 4ma, right here, 4mg cos theta is 4ma theta dot squared, okay? And that's what we're going to have. And that's going to be satisfied. Now, we also, we want it in terms of cosines and sines. So the trick is now, can we think of a way to get theta dot in terms of cos and sine? Well, we can, right? That's just here. Okay, we just rearrange that equation and make theta dot subject, substitute everything in, and we're done, right? So that's okay to do. The next bit, we want to show that while P and Q are still in contact with the cylinder, we want an expression for the tension. So similarly, all we're going to do is, instead of resolving vertically, we're going to resolve horizontally. So in this case, we're going to get 4mg sine theta minus the tension is equal to 4m. And this is going to be a theta double dot, so that's the transverse acceleration. Okay. Hope everyone's comfortable with radial and transverse accelerations. They are just simply, if I have a particle and it's moving in a circle, the acceleration, there's two accelerations. There's one towards the center and there's one sort of, what do you call that? Perpendicular to the center? Is that right? I don't really know, but we have this guy. It's called, the radial acceleration. This is a transverse, and basically this dude here is just going to be the mass, sorry, it's just acceleration, not mass acceleration. It's just going to be a theta dot squared. It's going to be a theta double dot, where a is the radius, right? So those are important to remember when doing these questions. But yeah, so that's just what we're going to have there, and we want an expression for the tension. So obviously we're going to rearrange that to get an expression for the tension. But notice that we're going to have theta double dot in there. So the question is, how again do we turn theta double dot into sines and causes? Because we want it in terms of sines and causes, right? Well, there's a number of ways to do it, but I guess the one that springs to mind the most is to just take this equation and differentiate. Because when we differentiate across by theta, what we're going to get is we're going to get the two will come down, so it's 14a theta double dot times theta dot. That's something to be careful about by the chain rule. Then we're going to get minus 8g sine theta dot plus 6g cos theta dot equals 0. And what we can do is we can cancel across the theta dot very carefully, of course. And we then rearrange and we have an expression for theta double dot. Substitute that in and we're done. Okay. So there wasn't that much to that question, really. What was important was knowing that we can differentiate the gravitational potential energy. I guess spotting that pi over 2 meant it was a right angle made things a lot easier, very fast. In fact, if you didn't spot that, I don't know if you could even start the question. There'd be too many things left unknown or whatever. But yeah, this was kind of interesting, and as step questions go for mechanics anyway, this was easier than most. So I mean, we all know that question 1 is going to be the easiest on a paper. But what about the mechanics questions? Is question 9 usually easier? Who knows, right? But I really like this one, so I hope you guys do as well. Thanks for watching. Hope this was helpful.